Hi everyone, today I am re-recording a webinar that we just did about Redis, Geospatial data, and urban forestry. Our original recording did not actually take the live event, so this is a replaying of it. Apologize for that, there was a technical glitch in the rendering of the recording, and hopefully I'll convey the same information and the same energy as the live recording. Okay, so today's topic, as we mentioned before, is Redis, geospatial data, and urban forestry. And we're going to explore an interesting data set as well as go through some example code today. So first, let's get a few housekeeping things out of the way. A little bit about me. I'm the technical marketing manager here at Redis Labs. I am a longtime Node.js developer. I've been working with Node.js for a number of years, and I've also been working with Redis for a number of years. I've published quite a few articles about using those two things together. I'm also a maintainer of the Node.js Redis client. I am based out of Edmonton, Alberta, which will be relevant as we go on in this particular presentation. And I'll show you what I look like. This is me, and you can see my dog who's hiding out in my shirt because he is cold. So let's go on and talk about what we're talking about today. First, we'll go over a little bit about Redis, Redis Labs, and Redis Enterprise and what those things can mean. We'll talk about our subject data set, the challenges of geospatial data, how Redis manages geospatial data, and frankly, those challenges, Redis-related geocommands, any geospatial modules that are out there, and then I'll go over some questions which were received in the original broadcast. So about Redis. Redis is an open source, in-memory, NoSQL database that has a variety of structures that are very simple yet very powerful. It has client libraries in over 50 languages, and many of those languages have multiple flavors of client libraries. So any way you program, you're likely to find something that'll work for you. Redis is known for being high performance. It was voted the most loved database on Stack Overflow last year. So that's a little bit about Redis. And then let's talk about Redis Labs, which is my employer. It is the home of Redis. We sponsor the open source project, and we employ the creator. We contribute about 80% of the commits to the open source project. We also provide Redis Enterprise, which is highly available, enterprise grade. It enhances the open source with high availability, multi-node and multi-shard clustering. It's available both in on-prem and cloud-based offerings. Redis Enterprise is able to achieve high performance, 1 million operations per second with 7 millisecond latency using non-exotic standard AWS instances. So it can provide the performance that you need. Moving forward, let's look at our example set. First, I want to talk about where this is. I live in Edmonton, which is the northernmost city in Canada. There's other places that are further north, but this is the northernmost city, so it has more than 1 million occupants. It's fairly isolated, which means we've avoided tree blights. As such, the city keeps detailed information about all the trees that are under the city, and so they want to make sure that it maintains a healthy urban forestry. In that, we have detailed 342,000 trees in the data set. It's part of the Open Data Initiative that Edmonton has put up. Here's the, let's look at the website for Open Data. I suggest that you look either at Edmonton's or your own Open Data initiatives in a municipality near you. There's a lot of great information there and a lot of things that you can really learn and gain insights from. And it's available in pretty accessible formats. And the format this one then is in JSON. It's a little bit odd, and we'll talk about that a little later. So, like I said, go for it. If you have the opportunity to work with any of this stuff, it's a really rewarding experience because oftentimes you're very related to the data, which is sometimes odd that you do that. Let's just talk about geospatial data for a second. Geospatial data is notoriously tricky. Latitude and longitude are not necessarily made for small objects. When they were really invented and established as a measurement system, they were talking about things like navigating boats into harbors, not the position of something that's a few centimeters wide. So that becomes getting into high precision floating point numbers, which if you've ever worked with can be pretty tricky, as they don't behave as you might anticipate always. And one thing that you might see naively is, latitude and longitude can be represented as a grid from a mental standpoint, but that doesn't really work because the Earth is not flat and math is difficult. So let's take a look at this example. St. Petersburg, Russia is at 60 degrees north, and 1 degree of longitude is equal to 55 kilometers in width. And Quito, Ecuador, which is at the equator, 0 degrees, 1 degree of longitude is equal to 111 kilometers. So there's a huge difference there. As you approach the poles, you can see the longitude getting smaller, and it's not an equal distance. So the grid concept doesn't really work. You can kind of look at it as like, especially as you go towards the equator, you get into latitude plus or minus 1 latitude or longitude. Doesn't represent a square, but kind of a deformed trapezoid. And it exaggerates as you go towards those poles. So the way you calculate this is the Haverson formula, which this is what the Haverson formula is. However, if you're like me, this is terror-inducing, but just don't panic. Redis will help you out with that. Moving on, there's some more things that we can talk about with latitude and longitude. One of the common patterns that you want to find is the number of points within a radius of something. And so you have the Great Circle, or the Earth, and then you're trying to find a radius on top of that. As you can imagine, the math gets a little bit hairy. So don't panic on that. One point I do want to talk about is that the Earth isn't actually a sphere. It's a ellipsoid. For all intents and purposes, in Redis and what we're going to talk about, we're going to treat it as a sphere, which introduces some amount of play to the calculations. So you should be good for most things that are not, involving human life. I wouldn't navigate a car with Redis data or a plane or something along those lines. But for locating something nearby, it's perfectly adequate. So moving forward, let's talk about GeoHash. GeoHash is really clever. GeoHash is how Redis mitigates a lot of these complications. It's a public domain coordinate representation system. It has a number of interesting properties. The way it achieves this is through a base 32 system. It goes A to Z and 2 to 7 in its representation. Here's an example. And with that, you can see that particular GeoHash represents this particular coordinate. And what is really fascinating about it is that a variable length of a GeoHash can represent varying precision as well. So it goes from the least precise on the left to the most precise on the right. So a shorter GeoHash will represent generally the same location, just with less precision. And the way it does this is it encodes even bits as a longitude and odd bits as a latitude. So as we remove things from it, we're actually affecting both latitude and longitude. It's not like the first 4 characters represent this and the last 4 represent that. It's interleaved. So let's see how this kind of represents things. We're going to go over to an example I have pre-set up. This is geohash.org, which is kind of the definitive representation of GeoHash. You can see in this box here we have the coordinates, and in the URL bar we have the different the GeoHash representation, and I'm going to illustrate how the precision works. So let's see here. You can see this is Edmonton, and I'll zoom out for those who aren't familiar with the location. Here we are in North America, and then I'll zoom back in for our example. This is something that's right outside of the city, and I'm going to start removing some characters from the end of the GeoHash and watch the coordinates. So let's take 2 characters off. You can see the location remains pretty much stationary. So this updated when I reloaded the page. I'll take a couple more characters off. Still pretty accurate. You can see we've dropped the number of decimal points of precision, but we're still in the ballpark. 2 more characters. You can see the pin has moved a little bit, but overall it's the same location, and we're down to only 5 characters here. So let's go down 2 more. Yet again, we're still within the bounds. We're still in Alberta. We're still pretty far off, but it's still representing the location. And as an extreme example, let's drop down to just one single character. Now, it looks like we're right in the ocean, but if I zoom out, you can see that we're actually just in a bay north of Canada. So we're still representing a location with a single character, which is really interesting. And we'll see how we can leverage that later on. So let's talk about how Redis stores these things. I'm going to talk about sorted sets, ZSETs or ZSETs, and then we'll talk about how those commands are manipulated. This is important to know before we get into the depth because they'll kind of cross over. A sorted set is basically a unique string with a score all held under one kind of unifying key. When I say that, what we have is a unique string that can't be repeated throughout that unifying key, but score repeats are okay. And the way I always explain this is if you think about something as two members, each one of these is a unique string or a member. The two members we have here are Bob and Sue, representing people. They can both have a score of 14, right? But Bob can't have a score of both 10 and 14. Does that make sense? I hope so. I like to think of it as just a set of items, like a mathematical set, with a natural order applied to them. When we look at this, geo commands are somewhat unique in that they borrow the sorted set data type. Most commands in Redis have their own data type associated with them. The whole set of commands may have one particular data type. But Geo borrows its structure from sorted set. So the scores represent the Geo hash. Instead of being represented as base 32, we're representing the bits inside that score. So the interesting thing about that is that Geo and ZSET commands can be used on the same set of data. So it's not very useful to use if you have a sorted set that has other values in it. It's not usually useful to use Geo on it, but the opposite is true. We'll be using some sorted set commands in Geo. So keep that in mind as we explore the first command, which is very useful, GEOADD. If you want to follow along, this address, this bit.ly address, is a link to a gist that has the source code for the importation of it, and then we'll work with the Redis CLI as we go along. So GEOADD has this kind of sequence of arguments. First is the overall key, then the decimal representation of the longitude, followed by the latitude, and then finally the member. And let's take a look at the source code real quick here. So this is just a short importation system, and we have about 50 lines of code here. And this is all Redis overhead. We're bringing in a few different modules, the Redis module, async. We're getting the actual connection information from the command line, and then we have a few strings here, which we'll go over in a second. I'm creating my client connection to Redis. And I'm going to load in the trees here. And as you'll see, we're going to do this in a second. Let's just actually do this right now. So we'll do node index.js. And like I said, I'm going to bring in my connection. All right, I have everything stored in a JSON file. And we should see the trees loading. And then we'll see it all bringing across. So while that's working, we'll take a look at the rest of the code. I'm bringing in a number of different items asynchronously from the JSON file. As you can see, this JSON file is basically in a number in arrays, so the array columns are relevant, and these are the different arrays, values for each column in the array, I should say. There's a unique ID in each one of these, so I'm assured that each tree will be unique, and we'll talk about that for a second. So our member in this case is going to look like this, and I'm just concatenating everything together, and I can be ensured by uniqueness of this by this last column here, this 0th column, and then I'm going through and importing a couple different ways. The first bit here is I'm going to import it into the index:all thing, and then I'm going to bring in the longitude and latitude, followed by the tree data, which will look like this. And we can take a look at this in a little bit better. This is what this looks like. And so we have the common name, the scientific name, the diameter, the setting, and then that unique ID. And then I'm actually indexing it in another way as well. So I'm going to index it by that common name. So as you can see here, I'll have index plum Chinese, and this will allow me to find all the Chinese plum trees as an example. And finally, I'm doing a ZINKERBY, which will just tell me a shorthand way of looking at how many trees we have of a particular type. And then once that's complete, I will tell you how many million operations we sent through, and we'll quit. So you can see that just finished. We did about a little over 1.7 million operations to bring in all those data, because we were sorting things and you had a few commands there. So let's take a look back at this. You can see that. One thing I want to touch on, this may seem a little bit weird to you if you come from a SQL background, because you're used to working with normalized, deduplicated data. Please forget that. We're in the NoSQL world right now. The key way to look at this with data denormalization is that you put data into your data source or database the way you want to pull it out later on. Duplicated data is just fine. For our situation, we're going to create multiple indexes, and those indexes are how we want to pull them. And then, because Redis doesn't impose structure on keys or members, the indexes can have spaces and commas and all sorts of different characters into them. Don't worry about that. I know that's a big leap for a lot of people because they want everything to be in nice, columns. We don't have to necessarily worry about that. So let's go as an example of a couple different things. Let's take a look at the zrange and zcard command. So I'm going to go back over to my command line here. So let's do zcard, which will tell me the cardinality, or the number of items in it, and tree indexes. Okay, and this is the different indexes we've created. And if you remember over here, the zcard, this tree indexes, is just a count. We're using the sorted set here. So let's do a zrange to actually see what's in there. 0, we're going to start with the 0th item, and then we're going to go to -1, and that's the stop. And the way I think about this is that with a sorted set, you can use a negative number to represent the last, because it kind of like loops around, okay? And we want to know the width score, so we want to know the number of items that we have in each different index, okay? I forgot the key. Let's try that. Okay, so this is the different items that we have. So as you can see, we have the most green ash trees in Edmonton. And then we can see a few lonely trees up at the top. You can see that some types of trees only have one individual lonely little member. And those are, I don't know, I kind of find it quite sad that they somehow have gotten this far north and they're the only one of their type. I don't know. Let's take a look at the Douglas maple, though, as an example. Let's take a look at the actual index of Douglas maples. Now, we know there's only going to be a single one in it because Redis brings things in interleaved. So the second item is the count. So we can see here, as an example, American elm trees, there's 71,000 of those, but up here, this Douglas maple should only have one. So to do that, I'm going to do zrange again. But this time, instead of doing it the tree indexes key, I'm going to do the Douglas maple. And let's make this bigger for our viewers. Okay. And then a little bit larger. Okay, so you can see I'm working down here. I want to find all of the Douglas maple trees. We know it's only one, but let's just do this to take a look at it. This will find everything. Remember that loop back? Okay, with scores will tell us the number, and there you go. Now, this is going to look a little bit weird, right? So you can see that instead of it being a count here, we've actually got this big number. Why is that? Because that is actually the decimal representation of a geohash. So, but you can see some information about the tree. It's Douglas maple. Here's the species name, the diameter, its setting, park, and then the unique value for it. Okay, so let's take a look at those a little bit further. As you can see with our zcard, we were able to see the number of items in any geo or sorted set. we did the Z range, and you can see that with the key in the loop around, that's there. And with scores gives you the not only member, but also the score. And we're using this on a geo, and you can see that big decimal number doesn't really make sense, but that's okay. Okay, so let's look at geohashes. Geohashes will tell you the representation of it, okay? So first you have a key and then a member. So let's go back over to our example. And let's take a look at geohash. The key that we're looking under is this Douglas maple again. And then the member here. Now, before, you could see we had that big long decimal number that wasn't very useful. This is our actual geohash value. And let's bring over to here. And we'll, just for fun, let's put this back into geohash.org. And as you can see, this is its actual location. It's in Rundle Park. And if we take a look over to the satellite view, we actually see that tree, that individual tree. Okay. Okay, so let's take a look again at the geo. We'll take a look actually at z-score. That'll make more sense to you. So let's do a look at the z-score here. And it should have the same actual values. So the thing to remember is that geohash versus geoscore are just different renderings of the same data. And so there's our big long decimal number. That's not very useful, but still good to understand that this is equal to this. And then let's look at the most useful of these, the GeoPos. And this is, again, just a different rendering. So we're going to go through, put these same arguments into it. And as you can see, that's a location. And if we were to put this into geohash.org, we'd see it come up with this number almost exactly. Okay. So moving forward, let's talk about the GeoRadius and GeoRadiusByMember commands. GeoRadius has the following signature. You have first the key, then the longitude, the latitude, the radius in a particular unit. There's many optional arguments. I'm not going to get into those. But you can also add distance and sorting. We will work with those. So let's take a look at an example, okay? All right, so I'm going to go in and do GeoRadius. And we're going to do index all. So index all has every tree in our data set, as opposed to this index maple Douglas, which just had that particular species. Let's use the latitude and longitude of that particular tree that we were looking at, the Douglas maple. And I'm just copying these values in. And then as far as radius, let's say within 30 meters. Okay. So this tells us all the trees within 30 meters. So you can see our Douglas maple tree right here. And that's the tree that we were looking at. And you can see that it's surrounded by Scots pines, it looks like. There's a few poplars as well. Let's add in distance and sorting to this. So with dist, and we're going to say ASC, so ascending. So we can see we got more values, although there's still 27 values, both of these there. Each one has a sub-value in this one. So we've assorted this, so we know we put in the location here, so within 0 meters is our actual subject that we were looking at. And 6 meters away is a Scots pine. Lots of Scots pine trees here, each with their own unique ID. But there's a hybrid poplar. That's kind of interesting. Let's take a look at that. So let's do GeoRadius. And again, we're going to look at index all. And actually, let's do GeoRadius. Let's do the poplar hybrid. How about that? So I'm going to put it in quotes here because we've got spaces in it, but that's just fine. Poplar hybrid. And we're going to reuse the same latitude and longitude as before. And pasting these values in. Let's actually go through and put that space there. And then let's see what's in the 100 meters of this. So this command's going to bring up all the hybrid poplars within 100 meters of the actual tree that we were looking at before, the Douglas maple. And let's do it with dist. And ascending order. Okay, so you can see here, this is where this command was issued. We've just got poplar hybrids here, and we can see the distances And because we were using this location, which was not exactly nearby the poplar hybrids, there's no 0 in this. The other interesting one is GeoRadius by member. As opposed to putting in a latitude and longitude, we're going to use a member of the overarching key itself and then find other members within a certain radius of it. It has the same optional arguments as GeoRadius. So let's go ahead and take a look at this in our command line. So I'm going to do GeoRadius by member. The key is, we're going to do the poplar hybrid again, index : poplar hybrid. And let's just take a look at, I don't know, this particular member. Excuse me. And let's take a look within 100 meters with dist and an ascending value. So yet again, we saw that, and this is the zero distance. So since we're sorting, we know that that's the kind of the actual location of this here. And then we can see that there's within 5 meters another one, and 13, and so on and so forth, all the way up to 98.28 meters away. So you can see that's all within that 100 meters distance. GEODIST is another interesting one. It'll tell you the distance between two different members of an individual geohash set. And so let's take a look at this. With this, let's take a look at this will be kind of interesting because it will show you the distance. And we're going to know it already, but it's good to know. So I'll do geodistance. And let's just take the distance between this member. But first we got to put in the key. So remember, it's index, poplar, hybrid. Then we have this one, and we need to close it in quotes. And let's just choose another random one and see how far they are apart. And we want to see it in meters. You can see those are 106 meters apart. Then if we go ahead, and that's interesting too, because this was in a radius, but different triangulations will give us different spacings. And we can also look at it in a different unit. This time we're going to use feet, so you can see 350 feet. So one of the interesting things about geo sets in Redis is that they're very easy to update. However, our data set doesn't really illustrate that because trees don't move very often. But geo is well suited to the moving data. Because this is a set, GEOADDing will just update the position. So as an example, if we were to take one of our trees and then change the latitude and longitude, and using the same key, it would update that entire set, so we would be able to represent moving data. So let's go ahead and look at that. Let's try that out on the command line. Let's take a look here. We'll do GEOADD and index all, right? And let's do a random number, 150, and let's just choose this guy here. And so this would update that command. Okay, so 0 means that we didn't add anything new, but we did do an update. So let's rerun this command that I just did, and we'll get a very different value because we've updated one of the members. So this is now 350. Okay, so this is interesting. I just did the index poplar hybrid, so let's do the index all. And this is going through why you would update them simultaneously. Sorry about that. So yeah, now you can see the difference is very large, 328,000 feet between them. But it goes to show you do need to update any additional indexes as well. That in this case, the two indexes are out of sync, and we would just do that at the application level, no problem there. So we can also remove something if we wanted to. That's using a ZSET command or ZSET command. Let's take a look at this, doing any particular one. Let's just actually remove the one we just updated. ZREM, ZRemove, and we'll do index all, and we'll just take this right from here. Okay, so now I've removed one item from it. If I rerun the previous command, you can see nil. So it's no longer presented in it, so they can't calculate the distance between two. So it works just as equally as well with the ZSET or a Geo command. Okay, so there is other options in Geo. Redis search is, or Redis search, depending on how you pronounce it, available at redissearch.io, is a module for full text searching and secondary indexing. A module is a component that you can add to the Redis service to implement new data types or to do more complex computations over those data types. So let's take a look at the code and how that works. It's a little different. You can still see the same basic format here in Node.js. And what we're doing is we're using ft-create to create a ft as in full text. That's where it originated as. And then we're doing a schema. And so as you can remember working with schemas before, it tells you how your data is organized. So a little less free-flowing. So we're putting in the common name, the scientific name, the diameter, and the setting. So we have numeric values and text values, as well as geo values. So once that has created, we would go through and pull in each one and do an ft add instead of a geo command here. And then we can add them in. And then we can take a look at the code. I'm not going to run this importation command, but let's pop over to that particular database and let's do ft.search. Notice that in Redis the dots become a underscore, just for compatibility with Redis syntax. So we have created an index called tree-search, and you can do some really interesting querying capabilities. So pine or elm, we'll do anything in a setting of a park, and we'll do a geo filter of a location, and I've got some stuff copied over. Okay, and we want to see within 1 kilometer, and we're going to limit it between 0 and 1,000. Okay, so you can see it came back quite differently. We were required only to get 1,000 items, but if you go through and look at it, you can see here's an American elm tree. That unique ID is rendered a slightly different way. You've got your location, what setting it's in. You can also see other trees as well. These are mostly American elm, looks like, but there's a Siberian elm. So it didn't necessarily search just for the exact value of elm. So there's some really powerful things you can do with it. It's a emerging technology right now, and if we take a look at it, you'll notice that there is a lot of stuff that's in this, and it's way beyond the scope of this particular webinar. So let's talk about the limits of it. It's currently a beta product. It works great, but we still call it beta because it is under development and things may change. There's a few things you have to work around at this point. You can't just get all the results in a particular geospatial area. You have to actually limit it by search terms right now, although that is changing from my understanding. One thing I do want to touch on is that it's not as light as just using the raw geo commands by themselves, from both a storage and a computation standpoint. So when you're looking at this, it is still much faster because it's in memory and it's actually really efficient than any type of spinning disk data store, but it does have limitations compared to the Geo system as far as ease of storage and computation. So look at you and evaluate your needs on it. If you want to go that option, it's a great option. If you need something very basic, Geo is a really good option as well. So let's take a look at some questions. These are some questions that came in during the webinar. Like I said, this is a recording about a week later after the webinar. How much memory does the dataset consume? This consumes about 170 megabytes using the geo type, sorted sets effectively. There was a question on accuracy. When I did touch on the fact that the Earth is not exactly a sphere, we talked a little bit about that. It's plus or minus 0.5%, so 0.5%. And so that's unavoidable given the current computations. But you're going to see that in most other forms of geospatial connections, and GeoHash is actually used in a number of databases as well. So it all has the common inaccuracies there. But like I said, for most applications, it's perfectly fine. The other question we had was about finding a point in a polygon. In our example, we looked at radiuses. Redis does not have a built-in system for finding inside a polygon. However, you can do it yourself at the application level. So the way to look at this is that GeoHash, as we looked at before, when I went through and looked at, I still have this up here so I can show you, you just have a single value. You can represent a very wide area. So by doing some calculations, you can actually figure out the fit of individual squares of geohashes and their size, and then seeing the matches to those geohashes. It's a little bit backwards way of doing it, but it can be done, and it would be good for a lot of low accuracy circumstances. Would be a really great way of doing it. Okay. So the other final question we had is how much data can we store, geodata can we store in Redis? This is a particularly interesting question. So when we look at it, we can have very large data sets. So each index would be limited by its shard, or the amount of space that you have in your entire open source Redis value. So at the current point, there's no way to have a shard or a geo index that goes over multiple shards. You could split it up yourself, certainly. So the thing to remember is 170 megabytes is quite small, even for large data sets. So it's not uncommon to see very large shards. You might want to restructure your data if you're concerned about storing a heck of a lot of geo data there. One thing you might want to consider is, instead of doing like we did, where we had all the data concatenated with semicolons, maybe just storing that unique value and then storing individual information about each, in this case, tree or the member, in other parts of the database. So that way you could spread it out over multiple shards. And the other thing you could do, in our case, we had index all, which had all the trees, and then you had indexes for each individual tree. Those could live on individual shards themselves. So so there's a lot of different tactics you could take to spread it out over multiple shards if you were looking to do that. But generally, this is pretty small data. You're not indexing huge amounts of every molecule on Earth. That wouldn't make sense. But for most circumstances, you can very easily store huge amounts of data in Redis, especially given this type of data structure. Okay, that's all I have for the replay today. It's a little bit shorter than the original, so I blew through it. If you have any questions, please contact me. My email address is kyle@redislabs.com. You can find me on GitHub, Twitter, or Medium at StockholmUX. And thank you for listening today.